So today I want to start chapter 7, and in chapter 7 we're going to talk about integration techniques among other things. Integration techniques. Before we get to 7.1, let's review all the integration rules that I have them on a handout. It's actually part of the notes. I'm not going to write all this down. It's written in my notes. It's also in the book. So if you recall, if you're integrating any constant, then it's constant times x plus c. Power rule, you add 1, divide by the new power as long as it is not -1. If it's -1, you get ln of absolute value of x. E to the x gives you e to the x. A to the x, it's a to the x, but then you divide by ln of a, and always add a constant, because when you do antiderivatives, your solution or your answer is always in that. Integral of sine is negative cosine. Cosine is sine. Secant square is tangent, because tangent is derivative of tangent is secant square. Cosecant square is negative cotangent. Integral of secant tangent is secant. Cotangent cosecant is negative cosecant. And tangent is ln of absolute value. Again, you can easily see this because tangent is sine over cosine. And then you can do substitution, u equals cosine, and it's going to give you that. Cotangent is ln of absolute value of sine. 1 over 1 plus x squared is tangent inverse. 1 over a squared plus x squared is 1 over a tangent inverse x over a. Again, you can do that by substitution. And then 1 over square root of 1 minus x squared is sine inverse x. And 1 over square root of a squared minus x squared is sine inverse of x over a plus c. Okay, these are the rules of integration that we went over in Calc 1 and some of Calc 2. Next, we're going to talk about what we call integration by parts. Why do we need integration by parts? Because remember, these rules are not the solution for all integration. So integration by parts. So for integrals that do not fit into these rules that we went over, we use what we call integration parts. So here it is. If u and v are functions of x and have continuous derivatives and have continuous derivatives, then the integral of u dv is u times v minus integral of v du. Let's prove this just to see where this came from. So if we let u equals f of x and v equals g of x, then du would be f prime of x dx, because du by dx is f prime, and dv, again dv by dx is g prime, so dv is g prime of x dx. Also, if you differentiate with respect to x, u times v, remember u is a function of x and v is a function of x, so the product rule says we're differentiating f times g, and that's the product rule, which is f g prime plus g f prime, which means if derivative of f times g is this, then f times g, then f of x times g of x is the integral of this, right? Integral of f of x g prime of x dx plus integral of g of x f prime of x dx, derivative and antiderivative. Okay, which implies if you take this guy and move it over here, integral of f of x g prime of x dx equals, so this one equals f times g, f of x, g of x, minus that. So I'm basically minusing this, okay? minus integral of g of x f prime of x dx. So remember, u is f of x, g prime of x dx is dv. So integral of u dv equals f times g, which is u times v, minus integral of g is v, and f prime of x dx is du. And that's what we call integration by parts. So how do we use this integration by parts? We know the rule, now how to use it is a totally different story. So let's talk about that. So guidelines. For using integration by parts. Guidelines for using integration by parts. Remember, we think about integration by parts if all the rules that we know fail, okay? So the first thing we want to do is try, again, this is all in your notes, but I'll write it down, it's not too much. Try letting dv, so remember we're trying to do integral u dv, so we want to let u equal something and dv equals something else. So try letting dv be the most complicated portion of the integral that fits a basic integration rule, which is the rules that I just went over. Basic integration rule. If it's possible, it might not be possible. Then u would be the remaining part. U equals the remaining part. Okay, try that. If that doesn't work, then you try letting u to be the portion of the integrand, of integrand whose derivative is a function, remember we're going to do u and du, derivative is a function simpler than u itself, So make sure when you choose u and you find its derivative should be simpler than u itself. If it's more complicated, then that's not work. And then dv would be what's remaining, okay? dv is what's remaining. Again, it's more complicated than this, but that's a start, okay? That's a start. You need a lot of practice to be good at integration by parts. A lot of practice. So here's a few examples. Example 1, how to evaluate integral x e to the x dx. So according to the statement, we let dv be the most complicated part of the integral, which would be this guy, and that means u is x. So if we let u equals x, then du is dx, and you can see du is simpler than u, and then we let dv equals ex dx. So we're integrating, it's integral of ex dx, which is ex itself. So we're going to write this down. Remember the rule, u times v minus integral of v du. So u is x, v is ex, minus v again, ex, and du is dx. And you can see we started with an integral of x ex. Now we have an integral of ex. We know we did great. So x ex minus integral of ex plus c. Okay. Now the next example, we have no choice but to pick ln of x dx. So we have no choice. This has to be u and this has to be dv. No other choice. It's only one choice. If that doesn't work, then integration by part doesn't work. Okay, so let u equals ln of x and du is 1 over x dx. d equals dx. So v is the integral of dx, which is x. So this is u times v minus integral of v du. As you can see, u is ln of x, v is x minus integral of v, which is also x, and du is 1 over x dx, which is great because that's going to cancel out. So it's x, I'm moving the x up front, ln of x, minus integral of 1 dx is x plus, always add a constant if it's indefinite integral. Okay, example 3. Integral of e to the 1 over t square dt. So look, I can choose u to be the top or the bottom. If I choose u to be 1 over t square, then its derivative would be more, du would be more complicated, so we don't want that. So u has to be e to the 1 over t, and then all this guy would be dv. So if we let u equals e to the 1 over t, then du is e to the 1 over t times derivative of 1 over t, which is negative 1 over t squared dt, and dv is 1 over t squared. So we don't really need integration by parts here. As you can see, substitution would do, because we already have 1 over t squared dt is your du. So no integration by parts, okay? So just, let me rewrite this. So integral of e to the 1 over t squared dt, substitution, just u substitution would work. U equals, so du be e to the 1 over t times negative 1 over t squared dt. So all this is du. We need a negative. So we get negative integral of du, which is negative u plus c. So I was trying to do integration by parts, but we don't need that. We can just do substitution, okay? Number 10, page 490. Integral of ln of x over x squared dx. So again, obviously u is ln of x, and dv is the rest, 1 over x squared dx. So du, derivative of ln of x is 1 over x dx, and v is the integral of x to the negative 2 dx, which is negative 1 over x. So this guy is u times v minus integral of v du. So u is ln of x, v is negative 1 over x, I'll just put it here, minus integral of negative 1 over x, so that's a plus. Du is 1 over x squared dx. That's x. Du is 1 over x dx. And that's a minus. I don't know what I was thinking. Negative ln of x over x minus integral of 1 over x squared is, that was plus. Now it's a minus, sorry. Minus 1 over x plus c. Okay, so let's go over this one more time. U times v, ln of x is u, v is negative 1 over x, right there. And then minus integral of v, but because v is negative 1 over x, that should be a plus 1 over x, and du is 1 over x dx. And integral of 1 over x squared is negative 1 over x plus c, because you're using the power rule, okay? In case you're wondering, this is integral x negative 2, which is x negative 2 plus 1. That's where the negative is coming from, okay? Let's look at 24, page 490. integral of e to the negative theta cosine 2 theta d theta. So we can let u equals e to the negative theta. Let's try that first. If we let u equal e to the negative theta and du is, or dv, sorry, is cosine 2 theta d theta. If we try that, what do we get? Du is negative e to the negative theta d theta, and v, which is the integral of cosine 2 theta, is 1/2 sine 2 theta. So this is u times v minus integral of v du, e to the negative theta, that's what u is. V is 1/2 sine 2 theta, minus integral of 1/2 sine 2 theta, and du is negative, so it's a plus e to the negative theta d theta. So it looks like we went from e to the negative theta cosine 2 theta to e to the negative theta sine 2 theta. Okay, so if we do integration by parts on this, it's going to give us that, and then we might be able to move it over. So let's call this I. Okay, so let I equal integral of e to the negative theta sine 2 theta d theta. So I equal, again, we're going to do integration by parts again. Same thing, u and then dv. So u times v minus integral of v du. U is e to the negative theta. V, integral of sine, is negative 1/2 cosine 2 theta minus integral of v, 1/2 cosine 2 theta du, which is negative e to the negative theta d theta. So that would be negative 1/2 e to the negative theta, that's I, cosine 2 theta minus 1/2 integral of e to the negative theta cosine 2 theta d theta. So basically, so I want to go back here and rewrite this integral of e to the negative theta cosine 2 theta d theta equals, we got this 1/2 e to the negative theta sine 2 theta plus half I, half all this guy, negative 1/2 e to the negative theta cosine 2 theta minus 1/2 integral e to the negative theta cosine 2 theta d theta, which equals, let's distribute that. So you have 1/2 e to the negative theta sine 2 theta minus 1/4 e to the negative theta cosine 2 theta minus 1/4 integral of e to the negative theta cosine 2 theta d theta. You know, this guy is the same as this guy except for the constant. So if we add 1/4 integral of that, so we get 1 plus 1/4, which is 5/4 integral e to the negative theta cosine 2 theta equals all this guy, sine 2 theta minus 1/4 e to the negative theta cosine 2 theta. Now timesing by 4/5 would give us the answer. So if we do 4/5 times by 4/5 times this by 4/5, so you get 4/10 e to the negative theta sine 2 theta minus 1/5 e to the negative theta cosine 2 theta plus c. I did it differently. I let u equal cosine 2 theta in the notes, and it should have come up to be the same answer. Maybe not. Let's see. 2 sine 2 theta e to the negative minus Yeah, it is the same. I just had them separately. 2/5 instead of 4/10 and 1/5. It is the same actually. Okay, so this is what we call repeated use of integration by parts. We did integration by parts twice. And see how I did it in my notes on D2L, and I used u equal cosine and dv equals, it doesn't matter, okay? Okay, so here's a summary. I'm gonna summarize for you common integration by parts, okay? Things that happen often and what to do with them. And it's in there, so I'm not gonna write it down. Page 7 in the notes. Summary of common integrals using integration by parts. So if you have x to the n, e to the a, so power of x, and then either e sine or cosine. You could use, you could switch this. I showed you. You could use u equal e to that, or you could use u equal x to the n. So it's just, let's stick to that. U equals x to the n, dv is e to the ax dx, or sine ax, or cosine ax dx. So let u be the power of x and everything else is dv. Just for integration of the form, if it's xn lx, or xn sine inverse, or xn cosine inverse, use u equals ln, or sine inverse, or cosine inverse, and dv would be x to the n dx. So it's different here. For integrals of the form integral e sine or e cosine, use u equals sine. I did the other way around, it doesn't matter. And then dv is this. And then you might have to do wrap around like I did. You might have to do more than one integration by parts. So here's an example. How do we evaluate integral x sine inverse of x dx? So this fits into right there, x sine inverse. So we're gonna let u equals sine inverse and dv is x dx, okay? So that u equals sine inverse of x, dv equals x dx. So du sine inverse of x squared, my bad, it should be x squared, okay? Sine inverse of x squared, so it will be u prime over square root of 1 minus u squared, so x squared squared, and then v is the integral of x dx, which is 1/2 x squared. So this is u times v minus integral of v du, u times v, v is 1/2 x squared, minus integral of v, 1/2 x squared, du is 2x dx, dx over square root of 1 minus x to the 4. So this is, I'm going to move this guy up front, 1/2 x squared, inverse of x squared, minus, that cancels out, integral of x cubed over square root of 1 minus x4. It looks like we can do substitution. T equal 1 minus x4, dt is negative x cubed dx. So we need a negative, so that's a plus. So this guy would be integral of du, 1 over u to the 1/2 du, which would be u to the negative 1/2, add 1, it's u to the 1/2, so 2 root u plus c, which is 2 root 1 minus x4 plus c, and this guy will be brought down, 1/2 x squared sine inverse x squared, okay? Next, tabular integration. This is really neat. It saves you a lot of work, but it doesn't always work, of course. It works for certain functions. Tabular integration. It's called ladder method. This method works well for integrals of the form x to the n sine ax dx, x to the n cosine ax dx, x to the n e to the ax dx, and x to the n ln of x to the n dx. Here's an example. So evaluate the integral of x cubed sine x, which you can see fits into this guy, x cubed sine x. Okay, it could be sine, cosine, e, or ln, as long as you have a power of x in there. So this is what you're going to do. You're going to do alternate sign. You will see what I'm talking about. And then you're going to do u and its derivatives, and dv and its antiderivatives or integrals, doesn't matter. Okay, so remember we let u equal a cube in this case, and dv is sine x dx, or you can just do v prime and leave dx out, it doesn't matter. So u and its derivative, what's the derivative of x cubed? 3x squared. Derivative of 3x squared, 6x. 6 and 0. You stop when you have a 0. That's why you have to have a power of x, because eventually it's going to go to 0. Okay, if that doesn't go to 0, you can't use ladder, you can't use tabular integration. So stop when 0. So when u and its derivatives get to 0, that's when you stop. Now this means you always start with a plus and then they alternate, minus, plus, minus, plus. You see how we're going to do this. Antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine. Antiderivative of negative sine is cosine. And antiderivative of cosine is sine, and you stop at the 0 level. And then this is what you do. You start right here, and then you go diagonal, okay? You go down diagonal, and 0 doesn't go with anything, and even 0, if it does, there's nothing there. 0 times, and then you multiply. Multiply. Okay, so you multiply and bring the sign on. So plus x cubed minus plus minus plus, but you don't need that. So your answer would be plus x cubed times negative cosine x. So I'll put the negative up front. Minus 3x squared times negative sine is plus 3x squared sine x. And then plus 6x times cosine x. And then minus 6 times sine. And then don't forget to add a constant, and that would be your answer. Beautiful, isn't it? Here's another one. Evaluate the integral of, again, we have x to the n, and then those transcendental functions. So sign change, u and derivatives, dv and integrals. So u is x cubed, its derivative is 3x squared, 6x, 6, 0, e to the negative 2x dx. Antiderivative of that is e to the negative 2x divided by negative 1/2. And then 1 over 4 e to the negative 2x, and then negative 1 over 8 e to the negative 2x, 1 over, you don't need the last one, because, oh, you do, okay, and that's it. So it's always plus, and then you alternate. So this goes with that, these signs. So you go x cubed times negative 1/2 squared, which is negative 1/2 x cubed e to the negative 2x, minus 3x squared times 1 over 4, so minus 3 over 4 x squared e to the negative 2x, plus 6x times negative 1/8 is negative 3 over 4 x e to the negative 2x, minus 6 times 1 over 16 is minus 3 over 8 e to the negative 2x, and always plus a constant. Okay, now let's do integration by parts when it's definite integration. It's just a rule, just have to apply the limits. Integration by part. Definite integration by part. So if you have integral from a to b to dv, it's going to be u times v, but then you're going to do a to b minus integral a to b v du. Same thing, you just put the limits. So number 30, page 491. What's the integral from 0 to 1? It's e to the x over 1 plus x squared dx. So we let u equals x ex, dv equals 1 over 1 plus x squared dx. So if we do a product rule, it's x times derivative of ex plus ex times derivative of x, and then v is the integral of this guy, which is negative 1 over 1 plus x. So this is u times v minus integral of v du. We'll put the limits, of course. 0, 1, 0, 1. So u times v x ex minus, no, u times v times negative 1 over 1 plus x between 0 and 1 minus integral 0 to 1 of v du. Du is x ex plus ex, which is x plus 1 ex. This guy cancels out, and that's dx. So this is negative x ex over 1 plus x between 0 and 1 plus ex between 0 and 1, and this comes out to be e over 2 minus 1 if you plug it in. You need to show your work on the test, okay? Alright, 42 from page 491, and this is the last one that I want to do, okay? There's one more that I have in the notes, you can work it out yourself. Integral from 0 to t, e to the s sine, so you can see the upper limit is a variable, which is different from what you're used to. T minus s ds. So we're going to let u equals we can let u equals sine of t minus s or e to the s, it doesn't really matter. And then dv is e to the s ds. So du is going to be cosine t minus s. You're doing u by ds, okay? So times the negative ds, and then v is the integral of e to the s ts, which is e to the s. So this is u times v minus integral of v du between 0 and t, 0 and t. So u is sine of t minus s times v. V is e to the s. U times v minus integral of v du, which is all this guy, so it's a plus cosine of t minus s ds. This is between 0 and t, so if we put a t in there, sine 0 times e to the s is 0 minus e to the e to the 0, and then sine of negative s when s is t, so that's 0. When s is 0, that's sine t, so it's minus sine t, yep, plus this guy, let's call the I. So we're gonna integrate that again. Because this is e to the s cosine, we're gonna do one more to wrap around. So 0 e to the s cosine t minus s ds. So again, u equals cosine t minus s. dv is e to the s ds. So du is derivative of cosine is negative sine, but then times -1, so it's sine of t minus s ds. V equals e to the s, so I equals u times v, which is e to the s between 0 and t, minus integral 0 to t of v du, which is sine of t minus s ds. So if you plug a t for s, it's e to the t cosine 0, which is 1, minus plug a 0, that's a 1, and that's cosine t, minus integral 0 to t e to the sine of t minus s ds. So all this is I, so put it back there, plus I. So look what I have. I have the integral of 0 to t, the original one, e to the s sine of t minus s ds equals negative sine t plus I is all this, minus integral 0 t e to the s sine of t minus s ds. Now we bring this guy over here, that makes it 2 of them, 0 to t e to the s sine t minus s ds equals negative sine t plus et minus cosine t, and this is that over 2. That's what I have in my notes. Okay, so integral 0 to t e to the t sine t minus s ds is negative sine t plus et minus cosine t all over 2. That's it for 7.1.